Welcome to this SPE presentation. It's hosted by the DHRTC, at least it was called DHRTC. Charlotte will say a bit more about the new name of the organization. So this is the second season. This is the second half of this SPE season for us. There's 4 more presentations coming until the annual general meeting in May, and we're happy to see such a good turnout. We're over 100 people, 104 people, 115 people already. So that's pretty good. I'll just quickly introduce the presenters. We have 3 presenters who will be talking to us about the potential for storing CO2 in the Danish offshore subsurface. And the Danish offshore subsurface is mainly made up of chalk formations, so it's quite different to what you're used to. A lot of the people who are attending are working elsewhere, so outside of Denmark, on carbon storage, and most of those formations are sandstones. There's, as far as I know, no one else is looking into chalk formations. And these sandstones, about half of them are aquifers attached to oil fields or close to oil fields, and the other half are depleted gas fields, but again still sandstones. So the mechanics and quite a few things are quite different in those formations. So tonight you'll hear the perspective from Denmark, which is focusing both on sandstones, but to a large extent on chalk formations. So the first speaker is Charlotte Larsen. We'll talk about the knowledge gaps, technology and knowledge gaps that need to be closed before CO2 storage can be feasible and cost effective, particularly again in chalk reservoirs. She is a program manager for the CO2 storage research program at DHRTC. She worked 20 years with Maersk Oil and Gas as a lead drilling engineer and a well project manager, amongst other roles. And she's worked quite a few places on the globe, in Qatar, Turkmenistan, and Denmark, of course. And she has a master in civil engineering from DTU. And I think I'll introduce the other 2 speakers straight away, right up front as well, so that they can seamlessly move during their presentation from one part to the other. The second presenter is Marlene Hein. She will talk about the Bifrost project. So that's a specific project which is a cooperation between the DUC, which is operated by Total Energies, and Ørsted, which is the pipeline operator, among many other things in Denmark, and DTU, which is the technical university that is hosting this research center. So she will talk about this Bifrost project, and she's a project manager at hang on, I'm muted. Did you hear what I said actually or not? Yes. Yeah, okay. Suddenly I was muted. I noticed.
We heard you up until you started introducing Malene's background.
Yeah, okay. Yeah, so she's a project manager. And then she also worked with Maersk Oil and Total Energies as a geoscientist and a project manager as well in quite a few countries, again, Denmark, but also Qatar, Turkmenistan, and Kazakhstan. And she has a master's degree in geology from KU, Copenhagen University. And the third presenter, that's Hamid. He's our research lead. He leads almost all the research projects in DHRTC. He will talk about the main challenges and enablers for CO2 storage in chalk. He's managing at DHRTC various projects on applied research solutions, and he's also the connecting research lead between those 2 projects that I just mentioned, that Charlotte and Marlene are project managers for. And he has a PhD degree from Imperial College in London in Earth Science and Engineering. And he's actually worked at a few other universities as well, Delft, among others, and DTU, of course. So with that, I'm going to leave the floor to the team in DHRTC. So Charlotte, would you like to start and share your screen?
Thank you very much, Hans, for that introduction and for inviting us to give this talk here today. I will just share our presentation. I hope you can all see it now.
It's coming up.
Yes, I can see.
Good.
Yes.
So as Hans was mentioning, we have actually today changed our name for the research center, and I'll just say a few words about that before we start talking about the CO2 research we're doing. So up until now, we've been known, as Hans was saying, as DHRTC, Danish Hydrocarbon Research and Technology Center. But today we're changing to DTU Offshore or Danish Offshore Technology Center. So this name change is reflecting the change in our research portfolio, which have happened over the last couple of years, where we've started up research within, amongst other, produced water cleaning. We've started research within abandonment of oil and gas wells. And now recently, we've started up a significant sized program on CO2 storage. And as Hans was saying, we've also been awarded UDP money to be part of the Bifrost project, which Malene will talk about. And so with those things, we believe that it's time to change the name of the center so that it actually reflects the portfolio that we have now. And with this name change, there'll probably also be a increased focus on research within the energy transition and broader offshore related activities. So with those words, I will just move on to today's agenda as Hans was presenting it. And we will go through these three presentations after each other and leave some time in the end for questions. So first, I will start talking a little bit about unlocking the potential for CO2 storage in the existing oil and gas fields in the Danish North Sea. And most of you who are here today are probably very much aware of the increased focus on climate change, and a lot of countries have set themselves goals for the climate. Denmark is one of them, and I've noted 3 of those goals up here in the top left-hand corner of this slide. So there's an aim, a wish to reduce the emissions with 70% by 2030, to be climate neutral by 2050, and to secure CO2 storage by 2025. So CO2 storage is seen as an enabling technology to be able to meet all of these climate goals. And Denmark is very well positioned when we talk about CO2 storage. If you look at the Danish Energy Agency's homepage, there's an estimated storage potential in Denmark for between 12 and 22 billion tons of CO2, which is quite a significant volume. It's a volume that is about 400 to 700 times the current yearly emissions in Denmark. So there's really some potential for storing CO2 in the Danish subsurface. There's a map here that shows Denmark and where the potential storage is mapped out. There's both storage potential onshore with the light green and dark green dots here. There's nearshore storage potential, but then there's also the existing oil and gas fields that's marked with orange out here to the left. And you could say, why is it interesting to store CO2 in the existing oil and gas fields when you do have some areas that are either onshore or close to shore and thereby closer to the source of the emissions? But there are some very good reasons for looking at the existing oil and gas fields. I've listed up some of them. Sorry? I think maybe some people should mute their... Good, I think that's quiet now. Okay. So the reasons for looking at the oil and gas reservoirs for storing CO2 are, amongst other, that there is a very, very well described subsurface storage capacity. There's been decades of production from these reservoirs, and they're very well known, and there's a lot of data that's been collected. It's been modeled, and there's so much knowledge that can be piggybacked on for the CO2 storage, so that all this does not need to be, all this information, all this knowledge does not need to be gathered. It is already there. At the same time, because these reservoirs has held on to hydrocarbons, oil and gas over geological time, there's a very well proven gas tightness, a seal, very well proven seal, that is key to be able to ensure that the CO2 will stay in the subsurface over time. On top of that, there's a lot of existing infrastructure that can be reutilized to some degree. And one thing that I think is very important as well, there's quite a distance to shore and to inhabited areas. And this, I think, is very key when we talk about public acceptance of the CO2 storage, which is very important to get any CO2 storage project to fly. So therefore, we believe that it is very important to look at the old oil and gas fields for CO2 storage. And it's an opportunity, because we have all this knowledge already and the infrastructure to implement CO2 storage in Denmark on a shorter timeline than if we had to go out and get data for new storage areas. It doesn't mean that it should just be storage in Denmark in the old oil and gas fields, but it could be the first step for CO2 storage in Denmark. At DETU Offshore, or as we were called back then, DHRTC, back in 2020, we made a CO2 state-of-the-art study focused on the Danish oil and gas fields to be able to understand where there is, or if there were any knowledge or technology gaps to be able to make CO2 storage projects in Denmark. And I guess an important message from that study is that there are technologies already that exist for CO2 storage. You could start CO2 storage projects, and that does happen around the world as well, as we know. But there are some areas where we believe there is an increased, that there needs to be an increased knowledge in order to unlock the potential in Denmark. And Hans was talking about one of the key parts, that a majority of the old oil and gas fields in Denmark are chalk reservoirs. And there is a general understanding that CO2 storage goes together with sand reservoirs. But we believe there is not any research that show that it's not possible to do it in chalk. But there need to be created an extra knowledge about chalk and CO2 storage to unlock a large part of the storage potential in the Danish offshore. Another thing that came out of the state-of-the-art study was around the monitoring of the CO2 after it's been injected, both with respect to leak detection and plume movements. There are technologies out there available, but there needs to be a focus on developing more cost-effective monitoring methods. And I'll come back to that on one of my next slides. And finally, there's a gap around the wells, both the wells that are not going to be used for CO2 injection, but abandoned, how to abandon them if we put CO2 down into the reservoirs, but also understand whether some of the existing wells in the oil and gas fields can be used for injection. The state-of-the-art study also showed that there are a gap around the transport and the facility, the entire value chain when it comes to CO2 and getting it out to the injection points. There need to be a better understanding of the optimal injection pressure, transport pressure, temperature, CO2 impurities that take the whole value chain into account. I've made this yellow here because we don't believe that that's a topic that the research community can carry on their own. This is something that needs a broader collaboration to find the right balance here. So what we've decided to do here at DTU Offshore is to start a research program that focus on the three first topics that I talked about. And this is something we've been working on since this state-of-the-art study was finished a year ago. And we are now in the process of kicking off the first research. It was done a month ago. And the vision of the research we are conducting here is that we have to come up with a cost-effective and low-risk CO2 storage for depleted oil and gas reservoirs for the Danish offshore. So if you look at these three topics one by one, the first one being the chalk suitability for CO2 storage and the unlocking of the large chalk storage potential in Denmark, then we start off by trying to identify, is there any showstoppers at all for CO2 storage in chalk, or is there a limited room for injecting in chalk? Is there some specific conditions where the storage is suitable in chalk? And to do that, we have started off 5 projects that is going to evaluate chalk suitability from different angles. It is Hamid is going to talk a little bit more in depth about the challenges that there are involved in this in the end of this presentation today. But it's building on the vast experience we have here at DTU Offshore with research in the reservoirs, chalk reservoirs that we have here in Denmark. The projects is a collaboration between a lot of different partners. I've listed them up here to the right. There's GEO is involved, GEOS, DTU Civil Engineering, DTU Offshore, that's ourselves, DTU Physics, and DTU Chemistry. And our aim is that after years of research, we will be able to say if there is any showstoppers for chalk, or whether this is actually potential for storing in the chalk. And after that, we will then make a decision for a phase 2, and then start looking more in details into the different parameters that needs to be understood for the storage in the chalk. Monitoring of the injected CO2 is also a very important topic, both for a CO2 storage project to be able to live up to the regulatory requirements, but also for the public acceptance of the CO2 storage, to be able to verify that the CO2 is actually staying where it's supposed to be. There is 2 legs when we talk about monitoring. There is the whole understanding of how the CO2 moves in the subsurface, and then there is the actual detection of leaks from the storage at the seabed, leak through the formation, or leak through abandoned wells, if we're talking about an oil and gas field that's used for CO2 storage. We believe there is, based on our state-of-the-art study that there is a need to develop new methods for both legs. There are methods available. Currently, it's a lot based on 4D seismic. And 4D seismic gives some very, very good understanding of this, but 4D seismic is not the cheapest. And when you are in a CO2 storage scenario, you don't have the oil and gas revenue to pay for the 4D seismic. So it would be great if we could come up with some more cost-effective ways of doing this. We are at the center starting up some research on that. We have a project that's going to look at the seismic data to try, based on the historical understanding of the fields, to come up with ways to reduce the required acquisition. This is in collaboration with Leeds University that we're going to do this. In the same way, we have a project with Aarhus University to develop new sensors for detecting underwater the CO2. There are sensors out there that can do that, but based on that's optical sensors or based on pH measurements. But so this is going to be a lot more pointed, if you can put it that way, measurements. And finally, trying to come up with a completely new way of monitoring and mapping the CO2 in the subsurface and its way, if it should, against all odds, be moving up through the formations. We believe that's also very key to try and see if there is any brand new ways that nobody else has thought of. So that's kind of our involvement in the monitoring to try and improve the cost efficiency of CO2 storage monitoring under the conditions that are in the Danish North Sea. The last topic I'm going to talk about is the wells. In most of the Danish oil fields, there is a lot of existing wells, and you could split these wells into three groups. The majority of these wells would probably have to be abandoned before a CO2 storage scenario. So there it is. It's all about the well barriers and their them being able to sustain the CO2 on top of being able to sustain the normal hydrocarbons that they are designed for. So here we are starting up some research. Two of the projects to the left is all about trying to come up with new barrier materials. We have one project at Aarhus University where they're looking into adding some coal to the barriers. There's a project with DTI and Norse that's looking into biocementation, so microbial precipitation as part of well barriers. And finally, we're starting up a project with DTU Civil Engineering around shale as a barrier. And shale as a barrier is not a new thought. That's something that has been looked at around the world for many years. But we are looking into it in the DUC context and the way the wells are designed in the Danish offshore sector to see how can we activate this shale and get it into and thereby have a barrier that will last over geological time. So the other two legs we have when it comes to the existing wells is that some of them might be used for monitoring wells. And some of them might be reused for CO2 injection. Now, none of these wells has been designed to withstand CO2, and it's a completely, as you all know, a completely different load they will be exposed to than they were designed for. So, we were starting up a project with DTU Mechanical Engineering to make a empirical based prediction model looking at the tubing types that are used in the Danish North Sea to be able to predict if there is any remaining life or enough remaining life for CO2 injection in these wells. And at the same time, we are also starting up some research on some coating for these existing wells that can, so that the coating can be placed in the tubings and prevent the CO2 from corroding the tubing. And by doing this, we hope that we can help facilitate the reuse and of the existing infrastructure in the Danish North Sea, so that these wells don't have to be redrilled, because not only is the redrilling very, very cost heavy, but of course we don't want all the CO2 emissions that comes with drilling the well either when we're doing a CO2 storage project.
I think you may want to explain what the picture on the right represents as well.
Yes, the picture on the right, coming from a drilling background, I thought that was a bit obvious, but maybe not. It's bags of cuttings of the shale formation that has been collecting offshore while drilling the wells, and the aim is when doing this shale as a barrier project to use some of these cuttings to understand the shale that is in the different wells. So I think that's it for me. So basically, to sum up, this research program is all about unlocking the potential for the storage of CO2 in the chalk fields offshore, as Hans was saying, to try and reduce the uncertainties around it and improve the cost efficiency. And with that, I'll hand over to Malene.
Thank you. I will speak about the project Bifrost. And if you go to the next slide, I will just start with explaining what Bifrost is. That is the rainbow bridge that is connecting the world of the gods in Asgård with the world of the humans in Midgård. So you can say in the context of today, it's the bridge connecting our present.
You cannot see the slide here.
No? Why? What?
It definitely just continue.
Can you see it now, Hans?
No. It's black. Maybe it's on the second screen and you need to move it.
No, I was thinking about
it's
the same presentation.
I will try and share again.
And it's the nicest slide I have because it's the one with the most colors.
Yeah, the Bifrost colors.
Can you see this now?
Yes.
Yeah.
Going up, I think.
Yeah, it should be there now. Oh, it's on the.
Yeah, it's coming. It's something is moving. It's just. Yes, that's it. Yeah, I see it.
And it is beautiful. Yes.
Too many colors, maybe. Yeah. So you can see that Bifrost has been a popular kind of a thing in both in cartoons and of course in the old Nordic mythology. So as I was saying, it's the bridge connecting the earth and the realm of the gods. And I was thinking that it's a beautiful name for the project because you can see it as the bridge connecting our current carbon polluting presence with a much greener future. And you can see in the middle, actually, you can see the reservoir geologist with his geological hammer that he's venturing out to fight for the green transition. So it's a beautiful picture. Project Bifrost is financed by EUDP. That is the Energy Technology Development and Demonstration Program that is funding work by both enterprises and universities to demonstrate new green energy technologies. And the Bifrost project is a collaboration between DUC, which you will hear many times today. That's the Danish Underground Consortium, and that is currently Total Energies, Noreco, and Nordsøfonden, and they're producing oil and gas from a whole lot of wells in the Danish sector of the North Sea, and they're owning also key parts of the infrastructure. Then we have Ørsted, who owns the pipelines that are connecting the fields to shore, and then we have us here at the Technical University of Denmark, both DTU offshore and DTU management. And I'll just also briefly say later what DTU management is doing. So we can take the next one. Here I'm trying to summarize Project Bifrost in one slide. You can already click on the first. The project is focused on demonstrating the feasibility of transportation and offshore storage of CO2 in depleted hydrocarbon fields. And here, Charlotte was speaking about the whole DUC area. Here we're zooming in and looking at the Harald reservoir. Again, you can see the Harald field out there on the small map on the left-hand side in the bottom. Harald has kind of two elements to it. There's the Harald West Sandstone Reservoir, and there's the Harald East Chalk Reservoir. And that's important for this project because sandstone is seen as a more mature medium for storing CO2, whereas chalk is, as Charlotte was also talking about, is seen as a more immature medium that might require some more knowledge before kicking off CO2 storage. And if you click again, also related to this sandstone chalk element, you can say the differentiating factor for Project Bifrost is really that if you can prove that chalk and the depleted chalk reservoirs in the Danish offshore sector can really be used for CO2 storage, there's a significant possibility to scale up CO2 storage in the North Sea. And if you click again, for the innovation related to kind of the DTU offshore part of the study is very much related to proving up that depleted hydrocarbon reservoirs can be used for storage, and here especially for us it's the chalk. The reuse of existing wells and offshore infrastructure related to these fields, and then as I said, that you get this high scalability with if you can prove up the chalk. The last yellow highlight is up in the upper right-hand corner. If Charlotte clicks again, yes, you can see that the Project Bifrost is lasting 2 years. And after this, in 2027, if the project proves successful, in 2027, there's a possibility to start up injection of CO2 in the Harald West reservoir to start with. So, yeah, so the longer term vision for Project Bifrost is therefore to unlock a very significant offshore CO2 storage potential in Denmark. And as we mentioned already, it includes this repurposing of existing assets where you have already your depleted reservoirs, you have wells, you have surface facilities, and you have the infrastructure, the pipelines, etc. And as Charlotte was also speaking about, it's an opportunity to store CO2 in a part of the subsurface that we know very well through decades of oil and gas production, both static knowledge, dynamic knowledge about how fluids are moving in the reservoirs. So it's kind of an opportunity to kickstart the early CO2 storage in Denmark. Then also very important, we have already a very highly skilled workforce with experience in offshore operations that could be transitioned into CCS industry. And then again, the social acceptance part. If you have an offshore storage site, it's far from anybody's backyard, and it might play a significant role in how it's perceived. We all know there are difficulties in setting up large windmill parks or solar panel parks close to residential areas. So that is also where DTU management comes into the picture for the study. Thanks. Good. So zooming in a little bit more on where we are hoping to make a difference for this project. the scalability of Bifrost, hoping that the demonstration project proves successful, is very much related to the storage potential. So the first part of the storage would be in the Herald West sandstone reservoir, where sandstone is a less controversial storage reservoir. Then we will be able to scale up with storage in Herald East chalk reservoir if it's proven to be feasible to store CO2 in the chalk. And then finally, there's a long-term potential for really significant scale-up as this large portfolio of DUC chalk fields are ceasing production in the next couple of decades. Yes.
Oh, wrong way.
We went the other way. Now I will zoom a little bit into what we are doing here at DTU in connection with Bifrost. So, as I said, DTU in this respect is DTU Offshore and DTU Management. So DTU is leading 3 work packages, and we are supporting a 4th work package. The work package where we are supporting is on validation of the Herald West storage potential and capacity. It's led by DUC and supported by DUC Offshore. Then DTU Offshore is leading the work package on subsurface studies on the CO2 storage in Herald East chalk, leading the work package on monitoring technologies that I will also speak a little bit more about on the next slide. And then finally, for DTU Management, the socio-economic assessment that is related to this social acceptance and trying to understand what it means that we are moving the CO2 storage offshore to the depleted oil and gas fields. So that's really interesting, but it's outside the scope of this presentation. Again, zooming in on the 3 work packages that DTU Offshore is involved in. For the Herald West sandstone, we are supporting the DUC partners with some work on geomechanics and flow properties of the sandstone and some coupled flow and geomechanics simulations. On the chalk, the focus is really on a more detailed characterization and de-risking of some significant aspects related to CO2 storage. How is the reservoir behaving, the chalk reservoir behaving when you are injecting CO2? What does it mean for the injectivity? Chalk is a relatively low perm, or very low perm storage medium, but with a high porosity, so a high storage capacity potential, but this whole interaction with the CO2 needs to be understood, and any potential containment issues of the storage complex of Herald East specifically. And then the aim is to confirm the feasibility of the chalk, of course, for storing CO2. On the monitoring, so it's not something we've talked a lot about until now. I will just say a little bit about monitoring because Hamid is going to talk further about the chalk. So on the monitoring, it's, as Charlotte was mentioning, also a really central aspect for any CO2 storage. There will be regulatory requirements for monitoring that will also go further than just the injection period. So these requirements for monitoring over a long period can really have a big impact on the cost of the project, and therefore there is in general a large interest in looking at new and more cost-effective ways of monitoring, and that is both the movement of the CO2 inside the storage reservoir and any indications that the CO2 is moving outside, including, of course, the detection of leaks at the surface. So having an effective monitoring program is really also kind of your license to operate, because you need, of course, regulatory approval, and you need the public acceptance that you can show you understand what is happening in your storage reservoir. So this is really why we have included a separate monitoring work package, because you can say in principle it's part of the work on the sandstone reservoir and the chalk reservoir, but we've included a separate monitoring work package where we will start DTU Offshore will start to make a review of what is out there of novel and cost-effective monitoring technologies, and especially their applicability for the hard setting. And then the plan is to select 1 or 2 pilot technologies that we will then mature within the DTU Offshore Center. So I think that concludes. Yes, so I just want to say, of course, thank you to EUDP for funding the project. Thank you to the DTU Offshore team, and then to the Bifrost Partnership who let us talk about this today. And there are a lot more aspects to this. There are a lot of work packages that are not covered. We've zoomed in a lot on what we are doing here at DTU. So maybe there will be another opportunity later to hear more about the broader project. But now Hamid will talk a little bit more about the chalk part. I left you exactly 16 minutes.
That's the question. Only 6 minutes left.
Yeah, it's working. It's working.
Good. Thank you, Hans, for the introduction, and thank you, Charlotte and Mia, for explaining everything. So I don't need to say much, actually. What I'm going to say in the next 10 minutes is mainly talking some of the findings we have done more than a year ago around the state-of-the-art study on chalk. And the question was that whether chalk can be a place for CO2 storage, and we mainly focus, of course, on the fields we have in the Danish North Sea. We did a study more than a year ago and looked at different aspects of the CO2 storage in chalk as a sort of a new formation for storage. We could sort of review around 400 articles. We had several external interviews with many people from different universities, companies, and we had also many internal meetings. And the results are published in a review paper called Challenges and Enablers for Larger Scale CO2 Storage in Chalk Formations. And you can find it. It's open access article, so you can find it on Air Science Reviews. As Charlotte mentioned, that the drawbacks and benefits of storing CO2 on offshore hydrocarbon reservoirs are quite obvious. The main benefit that I like most is that we have a lot of data. What you see here is that a snapshot of a figure from Alex Colbert's paper that shows the 4D data from Halfdan field showing how the fluid or the seawater that has been injected moves into reservoir. So, and we consider this type of information is very, very useful for basically de-risking the CO2 storage in chalk reservoirs. And as you know, also we have a very thick layer of mud stone on top of the chalk reservoirs in various fields that could also help to secure the sort of containment of CO2. The topics we looked at for this review work was injectivity, storage capacity, wells, reservoir integrity, transport, and monitoring. I'm mainly going to focus on topics related to chalk because, for example, monitoring can be related to the different type of formations. I start with the storage capacity. We found several estimates of reservoir capacity, and that's more or less based on a static estimate of the capacity And we know that that is highly uncertain, and that depends on different storage mechanism that the system may experience during the storage and during CO2 injection. Of course, the operational condition governs a lot of, basically controls the storage capacity as well. Pressure, temperature, reactivity of the material in the reservoir, as well as the fluid composition, also governs how much we can store and with through which type of storage mechanisms. This is illustration of basically CO2 plume injection in a saline aquifer. What's important here to note is that when CO2 plume is injected after like 30, 40 years or 100 years, it will sort of move upward, the CO2 plume, and then we have a phase of residual CO2 between the wells and the plume, and also we have an interface between the CO2 phase and the formation fluid phase. So in our system, it can be hydrocarbon, and in saline aquifer, what is shown is basically fingers can form because of the when CO2 dissolves in water, it can get heavier, and that could form fingers. And if there are carbonate in the reservoir, this also dissolves the material. Whether or not this is the case in chalk is something we will look at it. And based on the permeability values that we have, this process may be very, or may not be very significant. But again, we are looking at the very long-term storage of CO2 in the subsurface. So even if there is a small rate of mixing at the interface, that may become important for the safety of the system. Of course, at the back of the behind the plume, we have the residual CO2 that will at some point reach an equilibrium with the reacting with the rock material in the system. One important aspect of the CO2 injection, the CO2 storage is injectivity. What is the capacity or injectivity of the system, and how sustainable is injectivity in our system? And we have looked at several sites, Ketsin or Snow, with good examples that they basically experience some injectivity impairment. And the reason, for example, in Ketsin was mainly related to microorganism activity. As know, it was salt precipitation. What is known by now is not only one process that may reduce injectivity. It can be a combined effect of different processes, including chemical effects, mechanical effects, and biological effects. We may have a dissolution, and dissolution may actually trigger fines migration. Or we may have even hydrate formation that all could reduce injectivity. What at the time when we did the review work, we didn't find any information on the pilot test in chalk. Here, just what you see is an example of injecting supercritical CO2 in chalk in both toll formation and ecophyst. Porosity doesn't change between before and after injection. Permeability, there are some experiments that showed increased permeability. I will show you another slide a few minutes showing why the permeability can increase in chalk. In terms of the storage site safety, we couldn't find clear evidence that there is a big problem in chalk. For limited experiments that were done on the basically DUC reservoir samples, both exposure of sample to CO2 or CO2 saturated brine didn't show any weakening. However, some experiments reported in the literature pointed towards increased weakening and deformation when the outcrop samples were exposed to CO2 saturated brines. This can be because of different type of chalk, or can be actually due to the using different protocols for the experiments. The cap rock integrity, again, there is not much known or there is limited information about the cap rock integrity, but at least there is information about the reservoirs that have been used for hydrocarbon production, whether they have a leaky cap rock or not, and that could be used for CO2 storage studies. I was in Portugal last December, and walking by the beach in Algarve, there are many nice features that you could see when you go to that region. This is a picture of rock arches at the beach, and these are carbonate rocks, and most likely you have seen these features in different parts of the world. And the reason this thing happens is mainly because of the groundwater flow coming and forming this sort of caves, and later on, of course, there is a sea coming to play and eroding the rock. And while I was walking, I was thinking, like, is this going to happen in the reservoir? Because I remember 1.5 years ago when we talked about CO2 storage in chalk, I heard there are some basically discussion about that we may form caves in the reservoir. But looking carefully at actually what is happening in the sea, that there are lots of processes that happens, and the question is that our reservoirs are going to experience this type of fluid dynamic insights. If we consider this is a groundwater flow, do we have fresh groundwater flow coming to our reservoir? Of course, we are adding CO2, but they quickly see, chalk is very reactive, so it quickly reaches equilibrium. So as long as we have no movement of fluid, we may not dissolve it. So we need some flow in the system in the long term, and that is something is important to know when we look at the CO2 storage in chalk. Just to give you an idea about what we do, we try to look at different scales for CO2 storage projects, starting from at the pore space that we have this nice coccolith. This is a picture that actually, when I moved to Denmark 6 years ago, Peter Frickman, I think he's now in the meeting as well, he showed me that. He said, hey, this is a coccolith on a single human hair that you can see. So you get an idea about the size of the particles that form chalk, but the material is extremely porous. So it means that there's a lot of void space in the system. However, the pore throats or the connectivity between the pore bodies are very small, so that reduces the permeability. So it means that we have a huge potential in terms of the storage. However, the low permeability of the system limits the mobility of the fluid that is in the rock. This is a good news, but at the same time, we have the chalk that is carbonate and it reacts. So if we have continuous injection of carbonated water into the sample, we make a different type of dissolution. This is a nice wormhole that you can see here. Was performed in one chalk sample. I think it was Austin chalk. And you may get with this actually increase injectivity if it happens near the wellbore. It may also impact the mechanical properties of the system. What is important to know for chalk is that chalk is among weakest type of rock when compared to, for example, sandstone. And that should be included in sort of when we look at the CO2 storage risk and potential. This brings me to my last slide, and that to basically highlighting that when we look at the CO2 storage in any type of formation, or even any other fluid storage, we would need to consider all different processes, including thermal, hydromechanic, mechanical, and chemical processes. And if we just consider one and separate it and do a test and look at the temperature effect, that may not give us the reliable results. So we need to design experiments, simulations that consider all these processes at the same time to have a reliable prediction for basically predicting the short and long-term performance of the CO2 project. So with this, I showing you a picture again I took in Algarve after the storm, and I thank you again for listening to my presentation, and I think we are ready to answer any question.
Yeah, thank you, Hamid, Charlotte, and Marlene for these fine presentations. There is time for questions. We can overrun a little bit, I would think. I'll start with the questions that were put in the chat already. The first one was from Frank Thomas. He is asking, what is the possibility of induced seismicity due to injection in chalk? CO2 injection in chalk. That's probably one for you, Hamid.
Yes, I can try to answer. I don't know the exact answer to this question. The way I look at it is that the seismicity, it may not be completely linked to whether it's chalk or sandstone. Of course, the mechanical property of the system is very different, but the structure of the whole reservoir and the pressure with which we are going to reach in the reservoir by injecting CO2 would govern the seismicity. What we are going to look, especially in Bifrost project, we are going to look at the impact of both pressure change as well as the temperature effect on the seismicity. So hopefully in 1.5 years, we can give a better answer. How big is the potential of seismicity in chalk reservoir?
It's a good question. It's one of the reasons why there is research specifically addressing these geomechanical aspects. So, and if I can make a comment, what you've been presenting, the three of you, is very much the research that is being carried out to de-risk the project work, and the project is a phased project. It's in a way a bit similar to the way that the Danish North Sea was developed from an oil and gas perspective as well. It was a phased development. It started with one small field, and then it was scaled up, and then it was scaled up further and further, while at the same time developing technology and doing research. And I think for the CO2 sequestration projects, because there will be more than one, it's something similar. It's a phased approach, and so the research goes in parallel with the project work, which includes, of course, actual field injection on a small scale first. Okay, so that was the thank you for that. So the next question is on the sandstone comparison of chalk with sandstone. So that was from Henrik Lünger Rothman. Does CO2 reactivity with the formation in chalk reservoirs push development in favor of using sandstone reservoirs, such as the Gassam formation? The numbers that Charlotte showed for the sandstones in the saline aquifers, such as in the Gassam formation, those volumes were enormous. But can you say a little bit about that, comparing sandstones with chalk reservoirs?
What I could say at this stage is basically the reactions, the chemical reactions in sandstone is going to be much less compared to chalk formation. That is one difference. But the other thing is also like the mechanical properties. So chalk is much softer material compared to sandstone. But the permeability can be different. So sandstone usually has higher permeability compared to chalk, which may not be that favorable for us. So these are the things that we are going to look at it. Actually, in Bifrost, the nice thing is that we are considering both sandstone and chalk reservoir. Both of them are depleted system, depleted gas reservoir, but we could, it's a good comparison to show which one is a safer place for storing CO2. One additional note to this is that when we talk about the depleted oil and gas reservoir compared to saline aquifer, we should note that there's, again, going back to the slide, very first slide I showed on the benefits, and that there is enormous amount of data available, and the wells and the platforms that are there for this system. Whereas for the aquifers, that of course there's a huge storage potential, but we have limited information about the system.
Yeah, Charlotte and Marlene mentioned that as well, that the reusing the existing infrastructure, so pipelines, wells, platforms, facilities, that's a major reason for to speed up the whole CO2 injection process to use the chalk fields. Let's move on. The next question is from Jan. In these projects, what are the rough percentages of experimental work and theoretical? So that's modeling and simulation work. So what's the split? How much is experimental? How much is simulation? Just a rough number.
I guess we can say for Bifrost there is both, but we will be planning in more detail exactly what work is needed once we have finalized kind of a preliminary phase where we assess which issues are most can you say, important.
But for Bifrost, maybe looking at the whole project, maybe the experimental work is around, for the whole budget is 20%.
Yeah.
I don't know the exact number, but for our own program, I think it's around 50-50 or 60-40. There are more experiments.
There's more experiments, especially here in the first phase, where a lot of it will be empirical.
Okay, then the next lot of questions coming, so we have to move fast, I think, is from Alex Crossland, and I think he points out that the crux of the matter, he says very interesting, thank you, and are there any issues related to repressurizing a compacted chalk reservoir? So that's the geomechanics part of it and everything. So repressurizing, what are the issues? Well, I think that's what you guys are going to find out.
Yes, I think what we guess at this stage is that we may not be able to reach to the original reservoir pressure that when we started producing these reservoirs. That's the initial guess. But we are going to sort of improve our models, run both dynamic model together with geomechanic models and use 4D seismic and try to predict what happens if we put sort of this loading stage, that when we produce gas and then continue with the unloading by injecting CO2 and see how the system behaves, the overburden, and whether we are going to activate any faults in the system. But it's a very important question for this project.
Yeah, the next one as well, that's from Nick, I don't have his surname, from the Netherlands, also working on CCS, and he's asking about how effective is the tertiary seal. In the Netherlands, they say they have the Techstein formation, which I think contains salt and everything as a seal, and that's much more effective. So the tertiary, we have the Munk Marl in Denmark, but can you say something on the geology side, on the sealing capacity of the overburden?
I'm not a geologist, so I should not say much about this. I think there are more
Marlene is.
Yeah.
Yeah, there are probably more experts in the audience.
Yes, but what we are going to look is basically we are going to look at the overburden overburden capacity in terms of leakage and so on after the reservoir deformation because of depletion, as well as looking at the CO2 impact on the capillary, basically looking at the capillary barrier of the cap rock. So these are the things we have planned to look at and see whether we can reach to sort of a trapping capacity in the reservoir for the cap.
I guess it's Mick Simpson. I can see him there on the screen as well. Yeah, Mick. I think without being an expert here, I would also say that even if you have a gas at shallower levels, it might not reflect what the status is of the seal today. It might be a much earlier event that has caused leakage. That said, there are fields in the DUC portfolio that we would maybe not choose as the first option for injecting CO2, but we see there are many fields to choose between where we expect that the seal will be efficient.
Yeah, and most of our fields, this is my own personal gas and oil experience in Denmark, most fields do not have a gas chimney or something that you can see on seismic, even at high pressure. So they have oil fields with gas caps, and particularly gas fields as well. They have the ability to be sealed. The cap rock has the ability to seal for at least methane, and viscosity of CO2 is similar to that of methane, I believe. So, okay, let's move on. The next question is, where are we? It's from Ade. Solarin, that's an interesting question also for more research, perhaps. Is there, under high pressure and potentially temperature conditions, a chemical reaction could be induced between the CO2, methane, and water? Are there any studies done in this regard?
I'm not aware of looking at both combination of the methane and CO2 reaction. That's a good question to look at. Yeah. Okay, so that's potential for research. Next question from Andrew Ross. Does the seabed subsidence that has been seen in these chalk fields, at least the depleted ones, increase the risk for the long-term sealing capacity of the cap rock compared to sandstone reservoirs? That's again similar to the question that we talk about, that of course we for the compacted chalk system we may not gain the same porosity, as well as the basically seal capacity may not be as high as what we started with. So that definitely would be different. Yeah. And that's something we're looking. Yeah. So these questions, they firm up once more that it was a good decision to have a work package that explicitly looks at the sealing capacity of shale as a cap rock in the programs that were presented. Next, a question from Arnaldo Gomez Caceres. Are you considering the effects of fractures in this kind of reservoirs? For Bifrost, we will look at the fractures as well. We mainly look at the impact of the fractures in the cap rock and see whether that has an impact on the sealing capacities, considering the capillary pressure as well. For the reservoir itself, we have one project that is looking at the impact of fractures on the reactions happening in the system. Okay, thank you for that. Then the next one, I'm not sure if I understand the question. How effective is frost chalk that's injected in well and plume transportation will not leak? I'm not sure I understand the question. Can you read it? Can any of you, or is Samuel here to explain perhaps what the question is about? No, sounds like Samuel's not there. Let's move on then.
So there's the comment from Rasmus Lang that he says for Harold West, they do rely heavily on reservoir simulation. That's interesting. And then some other just positive messages. Okay, here, since chalk is softer, that's a question by Frank Thomas. Since chalk is softer, do you think it has mechanical properties like salt? No, that can heal, for instance. You know, they have a certain plasticity. It allows, it can absorb any movements, and fractures can close, and that kind of thing.
We have creep, of course, in chalk, but that is again it's a time is depending on the time scale that we may have that sort of deformation.
Yeah. Okay. Oh, that's another question by Samuel. What measure of capping of the well is effective? What measures? I suppose that is for abandonment of wells, and yeah, no, it's combination. Could be for abandonment, but could also be the for wells involved in the CO2 storage. So it's a well question, I think.
So the wells, there are standard ways or traditional ways of abandoning all the wells, and these most of these are probably also valid when it comes to a CO2 environment. So those methods are the most standard being cement. One thing that we looked at in the state-of-the-art study as well was papers related to cement and CO2, and there was a little bit of a mixed message in the papers, where some says that CO2 and cement, CO2 is degrading the cement, and others saying that to some degree there might be an improvement in the cement barrier based on the CO2. So we are actually also looking a little bit into to that kind of cement and CO2 at the offshore.
Yeah. Thanks for that. And then I think this will be the last question from Milena Smitsgaard Brandt. No, there's another question that just came in. So it's the second last question. Would it be possible to use the chalk reservoirs as well as the sand aquifers, that overlay the chalk higher up in a single project, or would that be too complicated, or would that be unfeasible?
Well, let's say first of all, one thing we want to do by reusing the depleted hydrocarbon fields is that we are reusing the wells, so we don't have to drill new wells, and the wells are in the reservoirs. So that's one limiting factor. There might be deeper wells, but they would be exploration wells that have been abandoned already.
Yeah.
But of course, it is something that could be done, and it's probably feasible if you drill one well and use the shallower reservoir and drill some deeper wells. Or I mean, it's feasible, but whether it's economical is probably another question.
Yeah, and what it would mean for surface facilities and the injection parameters, etc. That would depend on the reservoirs.
Yeah, I think that on the map, Charlotte, that you showed of where the potential was, this enormous potential of 22 gigatons or something, it showed the location of the aquifers is just offset from where the oil and gas fields are. So they are not really in the same region. So that would make it very difficult to combine them in a single project. So the location where the aquifers actually are, the shallow aquifers, would require new wells because there's no infrastructure yet present. Okay, then I think this is I think the last question. Then we'll cap it here because it's already 15:15. So and that's a question by Rasmus Steenshoy, who asks, have you investigated the interaction and asphaltene deposition between residual hydrocarbons and CO2 in some of the Danish fields? So interaction between CO2 and residual hydrocarbons, including asphaltenes. That's quite a detailed question.
Yes.
Who can answer that?
Simon, who is not in the room now, but when we did this state-of-the-art study, there is also one paragraph talking about this issue. That many years ago, there was an experiment on looking at this, and asphalting formation was observed in the presence of CO2. So yes, that can happen, and that can impact the injectivity.
Yeah. All right, thank you for that. I think that completes the questions and the presentations and the question sessions. Just a few words from the SPE side, and maybe Adek would like to add on it. But the first one is that these slides eventually will be made available. We still need some approval from the operator, DUC, Total. We may have to take some of the information out, but most likely everything is going to be made available on our SPE website. So I recommend everybody to check out the Copenhagen SPE website and check out the LinkedIn pages for the SPE Copenhagen section. You can find all the information you need there. It has links to upcoming events. It has links to it will have links to the Copenhagen website where you can find those slides, etc., etc. So that's good. There will be a number of events still coming up this year. It's most likely presentations by, and those will be physical events actually, because so far during the Corona period we've had these virtual meetings, but we will start up the face-to-face meetings again. The first one is most likely going to be at CalCEP. They have modeling software, fluid properties and what have you. So that's in most likely in March. We still have to settle on a precise date. In April, we expect a face-to-face meeting at NRG. Yeah, is that focusing on CO2 as well, or?
No, it's a presentation of done by Inagi. And they will present the geothermal they have in Denmark. So that will be in the new office sitting with Maersk Drilling in Lyngby.
Excellent. Thank you for that, Mette. Yeah, that is really that will be very interesting as well, because that's the oil and gas industry. If we're transitioning away from oil and gas, then it's geothermal and it's carbon capture that will provide a lot of investment and work opportunities. Thank you for that clarification, Mette. And then in May, the annual general meeting that will most likely be hosted by Total Energies in their office near Noordhaven. Was there anything else coming up? Perhaps. Yeah, I think that was it. So thank you very much for everybody for attending. And thank you very much for allowing us to overrun a little bit in time, to go 20 minutes longer than we expected. But I hope you all enjoyed it, and thank you all for participating in this event. And we'll hopefully meet physically next month then, or a bit more than next month at CalCEP. Thank you very much.
Thank you.
Thank you.
Okay. Bye-bye.
Bye.